I'm Joe Zimmerman. I work on Filecoin research, and I'm here to tell you about PoRep in the context of Filecoin specifically. So what are the challenges that we face specific to the context of useful storage in the Filecoin protocol, and what are some new directions, some of which Nico alluded to before, in terms of fast retrieval and other important problems that we're investigating currently. And I should mention that much of this is work in progress research, so it may be a bit rough around the edges, and hopefully it'll be sort of seeds for ideas that we can dive into in more depth later this afternoon. All right, so a little bit more into the details of the storage model in Filecoin. So storage is divided into what we call sectors. Currently sectors are 32 gigabytes, although that number is subject to change depending on the PoRep parameters. And the way this works is the miner, a storage miner, will collect data from users, will pack that data into a sector, and then we'll seal that sector. This is the Filecoin terminology. That is, encode the sector using the PoRep encoding scheme before storing the data. And so, as you heard from Irene and Nico, this sealing is essential to enforce unique storage resources dedicated to each sector. So if you didn't have this, if you just had proof of retrievability, which is a common assumption in proof of storage-based protocols in general, where you just want to prove you're storing the client's data, then there's nothing preventing a miner from just storing zeros. Or if you sort of rule out that trivial case, you can say, well, the miner can just store encrypted zeros, to which only they have the key, and you wouldn't know the difference between storing encrypted zeros and storing some encrypted useful data on behalf of an actual user. So this is why, in particular, if we're relying on not just retrievability of useful data, but storage resources as the basis for the blockchain, for consensus and for the block reward, PoRep and not just proof of retrievability is essential. And so that sort of motivates the really strong requirements that we have in the context of Filecoin specifically. Now, again, as you heard from Nico, PoRep is used in tandem with what we call proof of spacetime, or POST. And so the way this works is that at some frequency, each miner, and this can happen randomly or at some regular interval, depending on the parameters, but each miner is sampled for a POST challenge. Some set of the miners, all the miner sectors, is subsampled. And then the miner has to prove that they're still storing the PoRep encoded or sealed data for each of those subsampled sectors. And the POST consists of a succinct, non-interactive argument showing inclusion of the sampled points in the Merkle tree in the commitment to the root to the encoded replica that the miner is storing. And so when this is done at regular intervals, the idea is we want to make sure that either it's done frequently enough or it's done in such a way that it requires a fast response such that the miner can't possibly, or it doesn't make sense rationally, for the miner to regenerate the data to meet each of the challenges. That is, they have to be storing the data the whole time because they don't know when and on what data we're going to challenge them. All right, so I won't dive into the details of the PoRep and POST model too extensively, but rather I want to highlight some specific challenges that we face in Filecoin. That both because of the more stringent requirement to enforce storage of useful data and because of the technical restrictions of the protocol, just the scalability target that we're aiming to hit, are particularly salient in the Filecoin setting. So the first issue is one we've discussed previously, which is that the encoding procedure, PoRep encoding, has to be expensive. And the way in which it's expensive is pretty flexible. It could be cost-based, meaning that the adversary needs to spend a certain amount of some resource in order to re-encode the data. Or it could be latency-based, meaning no adversary in the world, even if they have $50 million and build a custom chip, can possibly regenerate the data quickly enough to meet the challenge. So it has to be expensive. Now, if we make it expensive in the cost model, that's not ideal for the honest user. And we'll get to the details of that momentarily, but essentially, because the honest user has to do this at least once, it sort of enforces a bound on how often we have to require the adversary to do this in order to make the rational equilibrium work out. That is to say, it has to be cheap enough for the honest party to actually do it, to actually want to participate. But it can't be so cheap that the adversary can do it often enough to answer all the challenges. And so the cost model, the cost model is usually easier to prove. It usually gives us more parallelizable constructions, but it's not ideal from an efficiency perspective. Like, we would much rather have a strict latency-based guarantee, where it's just like you cannot possibly meet the challenge in time if you're not storing the data or most of the data. So this sort of motivates, this very sharp constraint here, which is, in the extreme case, sealing once, which is something that the honest party has to do regardless, has to be cheaper, and ideally much cheaper, than just storing the data for several months. Otherwise, the honest miners are just not going to store the data. And the problem is that hard drives are really cheap. I mean, that's great. We can get exabytes, tens of exabytes on the network potentially, because hard drives are cheap, but also because hard drives are cheap, we have to make sealing really, really cheap. Otherwise, it sort of devolves into proof of work. Like, we're essentially saying the better the more cost-effective your hashing setup is, your sealing setup is, the better you do on Filecoin, and that's not what we want. So it has to be cheap, but not too cheap. And so basically, the problem is sealing has to be really cheap. Sealing has to be really cheap, but it has to be expensive in some way. And so the ideal case would be it's really cheap, so we're not even depending on a cost assumption, but there's still this intrinsic latency bound. That means that the adversary can't possibly do this inherently sequential computation fast enough to answer the challenge. So that's sort of where we're at. Now, another challenge is one that we've heard about in previous talks as well, and this is what we call retrieval latency. So, sealing may be extremely slow, and in fact has to be extremely slow in terms of sequential time, especially for large sectors. So, typically what we want to show is if the attacker wants to re-encode a sector from scratch, they have to spend at least 30 seconds sequential, like a latency bound of 30 seconds. And if the PoRep is symmetric, that is to say, encoding is the same operation as decoding, or is a similar operation and it has the same types of cost profiles, then decoding or retrieving the original data, also has very high latency, which is not good. So if we want to enforce a bound of 30 seconds, then so this sort of falls into the analysis that Nico mentioned as well. You have this bound of 30 seconds. You have some loss factor just inherently from the PoRep construction, where you say, for example, the honest party to encode has to compute the entire graph, but the adversary only has to compute 20% of one layer. It's a pretty brutal constant here. And the AMAX, the hardware AMAX only makes this worse. So if the adversary can compute, let's say the adversary can compute SHA-256 in 4 nanoseconds sequential, and it takes us 12 nanoseconds sequential using SHA intrinsics on the CPU, that's another factor of 3. So if we want a symmetric PoRep, where encoding is the same as decoding, and we want to enforce a challenge response time bound of 30 seconds, then we have this ridiculous latency required for the honest miner to actually retrieve the original data, to decode the PoRep encoding. That's a big problem. And so this motivates a variety of new paradigms and new design choices for PoRep in general, one of which is asymmetric PoRep, which I can go into a bit more in a bit more detail later, but it's where essentially encoding and decoding are different operations. And the other is a new direction, which I'll allude to later as well, which we call wide PoRep, which is basically we want to provide an additional knob to tune to say we still want some relatively stringent latency bound, but we don't want we don't want the latency bound to depend on the parameters of the construction. So we don't want it to say, well, if we want 32 gigabyte sectors, you have to do 32 gigabytes times degree sequential hashes. I mean, that's that puts a very severe limit on the latency bounds that we can get relative to the decoding latency. So those are the two main directions that will lead us to, potentially lead us to fast retrieval, low latency retrieval, without imposing prohibitive costs in other areas of the protocol. And again, both of those will go into more detail later in the talk as well. But this is one of the key problems facing the PoRep design right now. The other problem is, again, one that we've discussed in previous talks. I'll go into a little bit more detail here. It's what we call regeneration attacks. Now, in a full regeneration attack, the adversary actually regenerates all of its data, every sector, every time it gets challenged. And this seems ridiculous, but actually, if you run the numbers, it's not as ridiculous as it seems. And if you challenge the miners at a reasonably sparse frequency, sparse enough to give you a scalable blockchain ultimately, and the frequency is predictable, then it actually does become a serious concern that the adversary will just go through and whenever it knows it's going to get a post challenge, just regenerate all of its data, so that no matter what the latency bound, it doesn't matter because it's not going to be required to respond to the challenge within the latency bound. It's just going to have all of its data ready by the time the challenge hits. So that's one type of regeneration attack. The other regeneration attack, of course, is what we call selective regen, which is the more intuitive notion where the adversary learns the challenge and regenerates only the challenge data, the minimum necessary to answer the challenge. And this is where the traditional latency bounds of PoRep come in, where you want to show that after they receive the challenge, from learning which sector and what data item in that sector they're challenged on, they can't possibly answer the challenge within the latency bound. So these are the two types of regeneration attacks we're concerned about. Right now in the Filecoin protocol, we have this sort of blanket mitigation, which is effective against both, but comes at a considerable cost for honest parties, which we call election posts. And the way this works is essentially, so contrary to the traditional challenge response paradigm, we don't sample a miner and then sample sectors and then challenge them on specific data items, but rather each miner, throughout the continuous execution of the protocol, every block in the chain is required to examine all of its storage, or some non-trivial constant fraction of all of its storage, to mine for winning tickets. Essentially, that's the language that we use. And so what we say is, well, you don't know when you're going to be challenged because you're always challenged. You're challenged every epoch, every step in the blockchain's execution. You need to scan your storage with that time-dependent state from the chain and see if you win. And so, if you try to do full regeneration, what that amounts to is you're regenerating all of your data every epoch, every step of the chain, every 15 seconds or 30 seconds. And if you're going to do that, you might as well just store the data. So that's where this sort of rationality assumption comes in, where you can't possibly you could, but it doesn't make any sense to do full regeneration because you're challenged essentially every epoch. And similarly, if you try to do selective regeneration, what you'll find is whichever sectors you decide to regenerate, those are the only ones on which you'll win. So it scales linearly. It doesn't help you to regenerate fewer because then you'll just win less. It'll be as if you were a smaller miner. So this is our current mitigation. It works quite well against both types of regeneration attacks. It comes at a considerable cost, though, which is that honest parties have to scan their entire storage, too. So we're spinning all these disks. We're burning all the processors, computing these proofs, and it imposes very serious constraints on how essentially the cost of participating in the protocol. That is to say, you would like, for a number of reasons, for participation to be essentially free. That is, in a robust and low latency Byzantine agreement protocol, for example, as you would use to maintain consistent state on the chain, you don't want parties to have to spend resources or consume latency in order to participate. You want it to be completely frictionless, because the faster you can do that, the more frequently you can have rounds of the consensus protocol, the more efficiently you can exchange this information, and the more rapidly you can achieve convergence of the chain. And separately, the less margin the adversary has to play around with sabotage, meaning increasing the cost for honest parties so that they're unable to participate effectively in consensus. So for any number of reasons, we don't want to impose this cost on honest parties every epoch if we can help it. And this is where, again, if we have some very strong notion of soundness that's completely based on latency, where we just say, we're going to challenge a miner, give them a certain amount of time to respond based on the chain state, and they can't possibly respond within that period unless they've stored the data, a large fraction of the data. So that's the goal. Now, I should also mention an attack that's somewhat specific to the context of Filecoin and useful proof of replication in particular. And this is also something that Nico alluded to in his talk, which is what we call seal stack. Seal stack, the term coming from the fact that we refer to PoRep encoding in Filecoin as sealing. And the way this works is you start with so the adversary, let's say, starts with some data they can easily regenerate, let's say all zeros for simplicity. They, posing as a client, they submit this as data to be stored. They make a deal with themselves to store the data. They encode the data, and then they get some replica data x1, the PoRep encoded data. They submit this as a client again. And if you want, they can encrypt it so that you can't tell that they're doing it. But they submitted it to the chain again, make another deal with themselves posing as some other Sybil. They repeat this k times, and they only store the final layer. And now, whenever they're challenged on, let's say, xi, they'll just look at their final encoding, and they'll decode only this section of the data and answer this challenge. And so now the idea is, if decoding is arbitrarily fast, as we would like it to be, functionality-wise, then we cannot escape this attack. Because if it's arbitrarily fast, they can just decode no matter what in time to meet the challenge. So no matter what the latency bound is on re-encoding, it doesn't matter. They can just decode to meet the challenge and store only a 1 over k fraction of the data that they actually claim to store. So that's a serious problem. And this, I think, gets to Ben's question as well, which is ultimately decoding can't be too fast. Retrieval can't be too fast. And so what we would like to do is we would like to say, we have this tunable knob, and there are a variety of ways we can get it, but there's this tunable knob that we can say, we would like to increase the parameters or modify the parameters so that decoding takes certainly longer than 4 milliseconds. It has to take longer than an honest party seeking to the location on disk to read it, but not so long that it's impractical to use in the network. And this is where Juan mentioned the figure of 400 milliseconds. Anywhere in between there is good. Like, we would like to say, decoding a particular entry must take the attacker at least, say, 50 milliseconds. That would be fantastic, right? If it must take the attacker 50 milliseconds, but the honest party can still do it in 200 milliseconds, that's sort of the holy grail. And it's hard, but we claim not impossible to achieve. And we'll see a few directions towards achieving this in the last few slides. All right, so as promised, here's one new direction that we're looking at. And this is what we call wide PoRep. So wide PoRep is still in the symmetric paradigm. So it's not an asymmetric PoRep. Like, decoding and encoding still look roughly the same. But the idea is we want to provide this tunable knob. So we want to say you can crank up this parameter to make both encoding and decoding slightly more expensive or less expensive in order to hit this narrow window between 4 milliseconds and 400 milliseconds. And so the way this works concretely, so you have, imagine that the entire data set, the entire original data, is divided into what we call windows. Let's say, intuitively you can think of a window as like 32 megabytes, let's say. So a pretty small chunk of data. And you still have these very large sectors, maybe 32 gigabytes, maybe larger, where in fact we're playing with some constructions where the sector size is a terabyte, but it's still divided into these very narrow windows of 32 megabytes. And within such a window, you do the typical symmetric PoRep paradigm, which is to say, in order to seal, you derive some randomness from the chain. You use that as the input to some depth-robust graph here. We assume that this depth-robust graph has to be significantly larger than the 32 megabyte window. So let's say 512 megabytes, 1024 megabytes. As we'll see, it often helps for this to fit in the memory of a GPU, for example, if you're going to use some memory hard function, as I'll show momentarily. But you can think of this as 32 megabytes, think of this as a gigabyte or thereabouts, and think of it as essentially, there's only one DRG in the construction. There's only one inherently sequential path, and that's a disk path. And all of the rest of the construction, the entirety of these layers is geared towards making every challenge here hit a large fraction of this DRG as dependencies. So concretely, what we do is we say, well, we first reduce this DRG via some parallelizable procedure, like just take the first k items and hash them and collapse them to the first item here. We first collapse it to some small constant multiple, let's say 2x or 4x, the mask. We then essentially amplify the dependencies. So we say, either using butterfly superconcentrator edges or expander edges, we connect these layers, which themselves are just singletons, they're not DRGs, but we connect them to each other, and we finally distill them down to this 32 megabyte mask, which we XOR in with the data to produce the encoding, as we would in standard symmetric PoRep. And what this aims to achieve is we have this tunable parameter where we can say the bigger the window and ultimately the bigger this wide DRG, the stronger the latency assumption. The longer a path of hashes that the adversary has to compute in order to recompute the mask. And so concretely, if the adversary drops some fraction of this storage, they get sampled here, they don't have this data. The rest of these layers are just here to amplify the dependence of this challenged data item. So maybe it gets enlarged to 2 items here, 4 items here. The adversary stores 1, so it's 3 items. But then it gets amplified to 6 items and 12 items. And eventually, it's a huge fraction of this layer that they have to recompute. And now, of course, they can't store this entire layer. And this is the key insight behind the construction. They can't store this entire layer or even an appreciable fraction of it because it's too big. It's bigger than the data, way bigger than the data. So if they have this budget of storage to allocate, which is all that makes sense rationally, all they can do is store maybe 1/8 of this graph, which is nothing. So they store 1/8 of this graph, and then we hit 3/4 of this graph. That's a very strong invocation of the DRG property, the depth robustness property. And so what that tells us is, by tuning these parameters, we can get a very large latency bound for a very small window without requiring any more overhead from the honest party. So without requiring the honest party to store, anything comparable to this amount of data. So this is one building block. It's sort of the essential lower bound on latency that we need in order to mitigate the seal stack attack. And this building block, in conjunction with what we call asymmetric PoRep, is what we currently believe is the best path to achieving low latency retrieval. Now, I'll just mention briefly also one other direction, which is primarily geared toward achieving different goals than fast retrieval, but is still interesting and could play sort of an auxiliary role in the new constructions, which is what we call Mempa Rep, or memory-intensive PoRep. And here you can imagine that we have an arbitrary PoRep construction, sort of parametric over the construction. So we can take wide PoRep, we can take SDR, we can take zigzag, any construction. But what we describe here is sort of a schema for making changes such that, so A, rather than just being based on latency of hashing, it's also based on memory hardness, either cost of memory access or latency of memory access. And B, the edges in the graph, or graphs, are determined dynamically. So in other words, rather than being a fixed DRG a priori, the edges of the DRG are determined by the outputs of the intermediate hashes. So when you hash, when you produce some node, you hash all of these nodes to produce it, and then you use the hash output here, just interpret those bits as indices, as a sample from the DRG distribution, which tells you what the parents of the next node are going to be. And so by doing so, you essentially force the adversary to have a general purpose random access memory. They can't bake it into the ASIC or the FPGA or even the algorithm in general. Like they can't do some a priori analysis on the DRG, some costly analysis to reduce the depth, because the DRG is going to be different for every instance. And in fact, they won't even have enough storage to store the DRG itself, those edges, without running the computation again. So these are the two key insights here. So basically, we have a relatively small sector size. So let's say 4 gigabytes so that it fits in, comfortably fits in memory on a GPU, for example. We determine the edges dynamically, and there are a ton of edges. And there are a number of tricks to accomplish this without blowing up the overhead that we can go into later. But there are a ton of edges, a very high degree. And what this buys us is essentially, we're forcing the adversary to have a machine with a general purpose random access memory with very high bandwidth. And what we're betting is that no matter what kind of chip they build, well, GPUs are already designed for that. They're not going to do much better than a GPU. And so, in theory, this could work either in the cost or the latency model, although I think it is best suited for the cost model just because the flexibility of ASIC design is so great that it's very difficult to prove latency bounds for memory access. It's not impossible, but we've had some difficulty doing it. So that's where we are. So we have wide PoRep and Mempa Rep, and some of the directions that we're pursuing from there are essentially compositions of those with asymmetric and other PoReps to achieve fast retrieval without imposing a high cost on the honest party. And that's roughly the state of the world. And with that, I'll take questions.
I have a particular question on the when of the wide PoRep.
Yes.
What is by itself that doesn't give you the major benefit that I see is that it gives you a smaller difference between an adversary, the generation time and the regeneration time, but because of you just do a single PoRep and you don't rely on multiple layers of PoRep. Right. Well, single DRG, so you don't rely on multiple layers of DRG.
Right.
But I am not sure if that helps for fast retrieval.
Yeah, so the way in which it helps is it amplifies the latency bound. So you don't need to require a very large sector in order to have a very large, arbitrarily large, in fact, latency bound for the attacker.
We had time, or we were moving on to another talk? So it would help if he would actually just go back to that construction.
This is the last one, so I think.
Yeah. Actually, mind going back to the construction and just.
I'm going to introduce some comments at the end, so we should go into Q&A, and then I can add some comments afterwards.
So yes, we can take 10 minutes to discuss this.
Yeah,
sure.
Okay. Yeah. Would you mind just going back to the wide PoRep construction?
Yeah, absolutely. Yeah. So the first layer is a wide DRG.
Okay. And so how is this wide? So this wide DRG is. Again, it's just like a wide DRG that's much larger than the data that we choose.
Yep.
Okay. And then how does the encoding work?
So you produce, so basically you start with some C, you hash along the edges of the YDRG, and then you just collapse it, so you take the first K into the first item, and so forth, to reduce it by a factor of K.
Sorry, so again, you take the you use a different portion of the YDRG.
Yeah, so you just want to, you just want to reduce it by a factor of K. We're not
What do
particular
you
on
want to
how
reduce it by a
happens.
factor of K?
So basically, you want to induce a dependency of each of these items on K of these items. So that a
So you
large
start with
interval.
this first singleton, and now you're going to, you're just deriving a mask and you're going to just symmetrical node. Okay,
Yes,
so,
that's right.
and these singletons, you use K of the nodes from YDRG as dependencies,
Right.
and in each singleton, you're going to use a different K.
Yes. Yeah, and you can just take them as sequential.
Okay, so first singleton takes first, and the next singleton takes the previous singleton and K more nodes from the YDRG.
It doesn't need to depend on the previous singleton, but it could.
Can you just explain explicitly what the encoding algorithm is, so it's very clear?
Yeah, so you hash, so this part's clear. Yeah, you hash along the edges of the here.
Now you have labels on all the nodes in the YDRG. Now you're encoding the first singleton.
Yeah, so now you take x0 through xk minus 1.
Sure.
You hash them all, and that gives you y0.
Okay.
You take xk through x2k minus 1. That gives you y1.
For each node of the
Yeah.
singleton. I see.
And so forth.
And what about the next singleton? That you're deriving from the previous one, or what?
Yeah, so you can, right, so it's, the edges are just from the previous layer. And you can imagine them, for simplicity, as butterfly edges. So it's just like you take, for zi, you take yi and
What do
yi.
you mean for simplicity? What are the requirements between the edges between the singletons? Do they have to be expanders? Do they have to be super concentrators?
So when I say for simplicity, I mean this is a construction that works, that has provable bounds. So if they're butterfly edges,
If they're
you get provable
super
bounds.
concentrated, then you're using the fact that butterfly is a super concentrator.
It's a weaker property technically, but yeah. Basically, it's just like here you take butterfly offset of 1, here you take butterfly offset of 2, butterfly offset of 4, and so forth. You don't have to repeat it to get a super concentrated bounce.
Oh, you're saying you're taking half butterfly graph instead of the double butterfly.
Right. And that suffices. I mean, I'm sure like you could get better bounds by using both halves or by using expanders, but this suffices. Basically, what you're trying to do is you're trying to induce the dependency of even a small interval here on a large interval here.
Okay, so what's the theorem that you proved?
So if you so basically if you drop so I should say there's no red coupling component here. Like for simplicity, we assume the encoding proof is perfect.
Okay.
We can modify the construction, but basically, if you drop a certain number of items here, and you're sampled on any one of them, then you must re-encode a large constant fraction of this graph.
So, but what if that's assuming that specifically I'm storing a fraction of the mask, but what if I'm storing some other advice from earlier on?
Oh yeah. So it isn't a doubling model, but subject to that restriction, if you store less than, let's say this is n and this is kn, if you store alpha n for constant
And if
alpha
I've left 1
1.
minus epsilon and pebbles on this entire graph,
Yep.
including the YDRG and all singletons,
Correct.
then I'm going to have to.
Then you will have to regenerate a long path in this DRG. I think it can be made essentially, by increasing k and increasing the size of the singletons in degree, you can make it an arbitrarily large constant fraction of the DRG. Although it may become ridiculously impractical.
So why wouldn't I just focus on storing everything in the first singleton? So
Everything here? Or
wait,
here?
because each singleton doesn't have dependencies on the YDRG, it's just on the previous singleton, right?
Yes, that's right. Sure.
Okay, so since the first singleton is much smaller than the YDRG, then
Yeah. So
would
yeah,
the analysis not boil down to how much of the first singleton I need to store?
Yeah. You can store even a 1/2 fraction here, but you'll still have to regenerate roughly half of the DRG.
Is this singleton strictly larger than data?
It's
Or is it singleton the same size of the data?
But the singletons are larger than the
Oh, singletons are large.
I see. So mask is the size of the data.
Right.
Wait, so then now I'm back to Nicholas' question. I'm a little confused. So if the singleton is larger than the data, then and the goal is to. So why does this give you a faster encoding time? Is it because the singletons are not DRGs? Like this wide, the time to encode this wide DRG,
Yeah.
which is what you need to do in order to extract the data. You're saying that can be much smaller than in this in the stacked DRG construction. And can you explain why?
Yeah. So essentially, because you can you can reduce the you can reduce the latency bound for the attacker arbitrarily by reducing the mask.
Reduce the latency bound for the attacker arbitrarily.
So basically, you want to hit this window between 4 milliseconds and 400 milliseconds.
We're talking about just the time to seal, basically, right? The time to derive this math.
Yes.
We want to make it really fast, or faster than what's currently.
Yeah.
And from what I understand currently, you have 11 layers of a DRG, and it's taking too much time, and there's no extra slowness. You're using fast hash functions, and so I'm trying to understand why this is going to be faster than 11 layers of small DRGs on this side of the data.
Yeah.
Because the data are divided in this mask. The idea is that the data are divided in the mask, and in the way that you go from the wide DRG to the first, so the singletons to the stacked stuff, you just use a piece of the DRG, of the large DRG. So in principle, you don't have to encode all the DRG.
No, I thought that for each node of a single
DRG,
right? You need the whole DRG.
That's right. So Ben is correct. So I should say this is not an asymptotic improvement over SDR. Asymptotically, it's a practical improvement.
So I'm just trying to understand exactly what the practical improvement is.
Yeah. So in this setting, what you're saving is you do not have to to get a certain latency down.
Yeah.
You do not have to do 11n or however many layers of sequential work. You only have to do the first layer of sequential work.
But the first layer is very large. So how large is the first layer?
It depends on the parameters.
Okay, so you can tune it, you're saying?
Yes.
And in practice, the gain that I see is that during the 150x now, so the difference between a single DRG. So I think the major thing that I see here is that there is in the SDR, it's you need to attack 1/10, and of this 1/10, 1/5, and in this you only have 1/5 of something large. So in other words,
let me just rephrase what you said a little bit.
Yeah.
So you're saying that in stacked SDR, the whole point of stacking is so that a small epsilon fraction of the nodes on the last layer have dependencies on nearly all the nodes in at least one layer before.
yeah.
Right? And what you have here is you have an epsilon fraction of the nodes in some layer, right, have a dependency on almost all the nodes in the wide DRG.
Yes.
So the question is now, so if the wide DRG is the same size as the data, then now you've just been able to prove tighter bounds on stacked DRG, essentially.
Yes.
But
Yeah.
it sounds like that you're not able to do that, but you need this to be much wider. So now the question I have is, what is wide? How much wider? Because then that is going to help me understand why you have to do less computation in order to get this same tightness.
Right. So I mean, let's say 8x.
8x.
Yeah.
So then at 8x, is that a lot? Yeah, so I guess you're saying that you now have, like, computing a wide DRG that is 8x is the same as computing 8 stacked DRGs, right?
Except it's so. Yes, if the degree is the same, but it's more parallelizable. So basically, we can offload. Yeah, so we can offload a ton of the computation to a high degree expanders or super concentrators. And so you can imagine, pragmatically, this could be done.
I think what you're saying, though, is that actually computing the labeling of this DRG, even though it's 8x the size of the data, is going to be faster than computing, than deriving the labelings of 8 stacked DRGs with expander edges with speed up. Is that right?
No, not necessarily.
Oh, no, not necessarily. Okay.
No. But the point is, for some values of the parameters, it could be.
Okay.
Because you can offload, because you can make this trade-off. This could be a relatively weaker DRG.
I see. So you're saying it doesn't have to be 80% robust DRG.
Right.
You're saying you can choose so you're saying you can play with the parameters of the DRG. Maybe you have a DRG which has weaker properties, but you just make it really wide.
Yeah.
And actually, even though it might be counterintuitive that it will be faster than encoded, it will be because you can have a simpler edge structure.
Exactly.
Okay.
And I think pragmatically, you also get a lot more parallelism because you can make the windows quite small. And so essentially, if you wanted to implement this completely on one of our sealing machines, you could say, well, I have 8 windows or 16 windows.
So sorry, explain. Maybe I'm not understanding the windows perfectly. So the windows are.
So let's say the data is divided into these 32 megabyte windows.
Got it. Okay.
So if you want 16 cores, let's say 16 cores to be cranking on sealing simultaneously, you get 16 of these 32 megabyte windows, and you could do each of them completely independently. That is, compute the DRGs completely independently, and then do the rest of the computation on the GPUs.
So the first, you still need to do 2 wide DRGs for 2 instances.
Yes, that's right.
Yeah. So that part you cannot really do in parallel, but after you do that, then you can parallelize this second step.
That's right. Yep. Yeah, but there we're exploiting the fact that CPUs have a lot of cores, right? And so because SHA has been so heavily optimized, SHA intrinsics have been so heavily optimized, you're essentially getting the maximum possible performance out of the CPU with a quite small footprint.
So just to summarize, so that I understand, there is the difference between if we compare SDR and this one, in SDR you have a large difference between the time it takes to encode and the time it takes to attack. Here you have a much smaller difference because you only need to do it on the difference in latency between the attacker and an honest generation is
right. It's parametric, right? It's parametric. So you can say so if you want a really robust DRG here, really good DRG parameters with a higher degree, then you get exactly that because then you don't have this factor loss in the adversary's advantage from the number of layers. Or on the other hand, if you want a weak DRG, then sealing becomes much cheaper. So you get one advantage or the other, maybe both.
I mean, sealing becomes much cheaper, but then you might have to do more expansion. So it's not clear if it's
no, exactly, but the expansion is parallelizable.
Yeah, so it's not cheaper in terms of it's cheaper in terms of clock time, but not in terms of computation. In computation, you might even end up doing more computation.
No, it's cheaper. It's cheaper in terms of computation too, because you can offload it easily to the GPU. It's embarrassingly
Sure, okay. But in terms of hardware, but in terms of computation steps, it could be higher. It's just that the way you spend the steps is in a cheaper machine.
I suspect it would also be fewer steps, but yes.
One question I have is, how does, let's say I have a 32 gigabyte sector, how does this translate in terms of numbers to this, just ballpark?
Numbers.
So my YDRG would be 8 times 32 gigabytes, and then I would have windows of 32 megabytes in that, and the single is how I would.
Yeah, so but you encode each window separately. So you never have to store 8 times 32.
But I do have to generate an 8 times 32 gigabyte YDRG.
No. You have to generate 1,000 8 times 32 megabyte YDRGs.
Oh, so the YDRG is per window, not
Correct.
per sector.
Yes. Yeah. And this is another advantage in terms of locality, right? Like you can, because you can do this independently for each
But I thought you can reuse the YDRG.
Could that be the same YDRG for every window?
Other one.
But you cannot you can't reuse it
I
verbatim.
thought that's the point that you were making.
Yeah, no, you can't reuse it verbatim, no. Because then you can deduplicate the storage. So it's, in total you will
No,
have...
because you can't store the YDRG. So
Correct.
I thought that you were saying that you can reuse the same YDRG to encode multiple masks up to almost the size of the YDRG.
You can't store it as long as because it's linear in your storage. If it's no longer linear in your storage, if you reuse it, then you can definitely store it.
Right.
I didn't understand.
So if you have a lot of sectors, right? Each of them are one replica. If this YDRG blows up your storage by a factor of 10, then you definitely don't want to blow up all of your storage by a factor of 10. But if you can use one single wide YDRG for all your storage, then you're just adding a small constant amount of storage, which you can totally store. So if you reuse this, then you have to be careful about how you reuse it. There's no factor of reuse.
Exactly. And the factor of reuse, like if you try to reuse it 2x, then it weakens your security to the point where you might as well use the 4x YDRG instead of the 8x wide.
That means you're adding a lot of computation now compared to SDR. Because in SDR, you pre-compute the DRG once and you use it.
You mean the graph?
So you have to regenerate those DRG every time. It's quite a lot of overhead.
Sorry, are you talking about the graph or the labels?
Talking about the graph.
Oh, the graph you can reuse, absolutely. The topology of the graph. Yeah.
Oh, okay.
Yeah. No, you can use the same graph topology. You just can't use the same actual data, label data.
Oh, okay. I thought you were saying you can't use the graph.
No, absolutely.
That
use the graph. Yeah.
Okay.
And in fact, like you can make the graph dynamic for better, heuristically better async robustness.
Yeah, it's just it's ridiculously very expensive. Yeah, to regenerate because like faster time.
Yeah, maybe there are some tricks, but yeah.
Okay.
You can absolutely.
So the graph itself stays the same. Just so you generate new labels, right? With wide, which out every time. Yeah, that's okay.
I think I get how you go from white DRG to singletons, and I get the sectors divided into windows. Are masks the same thing as the window, or how?
Yeah, so the mask is just basically alluding to the fact that in a symmetric PoRep you compute the mask in isolation without reference to the data, and then you XOR it with the data to compute the replica.
Okay.
As opposed to asymmetric setting.
Okay, there's a slight pause. I'd like to thank the speaker, and then we're going to do a transition for bringing food in for lunch, and then Juan will give a brief description of...
Just a few observations, expanding on some of the discussion or something.
And then we'll break into discussion. Thank you.
Thanks.